Sugar is a natural sweetener, extracted primarily from sugarcane and sugar beets. It consists of sucrose crystals, a type of carbohydrate found naturally in various plants and widely used to sweeten foods and beverages. Today, nearly 181 million tons of sugar are consumed worldwide each year. Producing such a colossal quantity is a complex task involving many steps. But have you ever wondered how sugar is made? In today's video, we'll visit several sugar factories to show you the incredible production process of this staple food, one of the most common ingredients in our daily diet. Stay with me until the end. I encourage you to like, subscribe, and turn on notifications to receive all updates. Sugar originated in India, where sugarcane was cultivated over 2,500 years ago. It was there that the technique for solidifying the juice extracted from the cane and transforming it into granular crystals was developed. Around the 7th century, during the Islamic expansion, the Arabs spread sugarcane cultivation throughout the Middle East, North Africa, and Southern Europe. With the great discoveries of the 15th and 16th centuries, the Spanish and Portuguese introduced sugarcane to the Atlantic islands and then to the Americas. In colonial Brazil, by the 16th century, sugar had become the country's main export. Production relied on vast plantations, mills, and the intensive use of enslaved labor. A painful chapter in sugar history. In the 19th century, the Industrial Revolution brought more efficient machinery for extracting and refining sugarcane juice, making sugar more accessible. It was also during this period that sugar beets began to be cultivated and used primarily in Europe, particularly after Napoleon's continental blockade, which deprived Europe of cane sugar produced in the Caribbean. In the 20th century, with increased production volumes, sugar ceased to be a luxury item and became a global staple. Simultaneously, debates intensified regarding the health effects of excessive consumption, including obesity, diabetes, and tooth decay, which fueled the rise of alternative sweeteners and less processed sugars. Approximately 80% of the world's sugar production comes from sugarcane, which is grown in tropical and subtropical regions. Brazil is the world's leading producer of sugarcane, with around 720 million tons per year, followed by India, China, Thailand, and Pakistan. Sugarcane naturally produces sucrose through photosynthesis, a biochemical process that takes place in its leaves. The plant converts solar energy into simple sugars, which are then transformed into sucrose and stored in large quantities in the stalk, commonly known as the sugarcane stalk. After planting, sugarcane takes 12 to 18 months to reach its first harvest. This time frame depends on the climate, the variety cultivated, and the soil conditions. During the last month, the sugarcane reaches its final height and begins to accumulate more sugar in the stalk. This period determines the quality of the juice. The more abundant and well-distributed sunlight the plant receives, the higher the sucrose production. Sugarcane can accumulate up to 20% of its weight in sucrose. Harvesting is carried out by specialized machines that cut and clean the stalks in real time, leaving segments approximately 20 centimeters long. At the front, feed rollers guide the upright stalks into the machine. Rotating cutting discs sever the cane at ground level. Defoliating rotor assemblies, equipped with blades, remove the leaves and the tips, leaving only the stalks. The leaves and straw are returned to the soil where they serve as mulch. Inside the machine, a set of chopping knives cuts the stubble into pieces of approximately 20 centimeters, an ideal size for transport and industrial processing. The chopped cane is transferred by conveyor belt to the vehicle traveling alongside the harvester. This system allows for continuous, uninterrupted harvesting. In Brazil, the harvest generally takes place between April and November, the period of the annual campaign. Once the trucks are filled, the sugarcane is quickly transported to the factory to avoid sucrose losses. Upon arrival, dump trucks or feeding tables unload the cane onto conveyors. The pieces are washed thoroughly with water to remove coarse impurities, soil, sand, and other debris. Next comes the defibrillation process. Rotating hammers crush the cane to break down the cells and more easily expose the juice. The juice is then extracted, one of the most crucial steps in sugar production, as this is where the sucrose-rich liquid is collected before being purified and crystallized. The shredded cane is conveyed to the mill, where it passes between rollers exerting high pressure. This crushes the stalk fibers and releases the juice, which flows out through chutes. The bagasse is transported in conveyors to be used as fuel in boilers. At each mill, a portion of the bagasse is re-moistened with hot water to maximize the extraction of residual sugar. This is the imbibition process. The collected juice, called raw juice, is a cloudy, greenish-brown liquid, still containing many impurities, sand, bagasse fragments, dissolved organic matter, and microorganisms. It therefore immediately proceeds to the next stage: purification, processing, and clarification. The first step involves heating. The juice is then passed through large heaters where it exceeds 100 degrees Celsius. This temperature increase destroys microorganisms and thins the juice, making it easier to process. The pH is then adjusted. The factory adds hot milk, which neutralizes the sugarcane's natural acidity. This correction also helps many impurities clump together into flakes, making them easier to remove. Some factories also apply sulfur dioxide, which helps clarify the juice and remove even more unwanted particles. The clarified liquid is then directed to enormous tanks called decanters. In these tanks, the heavier impurities settle to the bottom and form a kind of sludge. The clear juice rises to the surface and is carefully drawn off. The settled sludge is usually filtered, and the solid residue, the filter cake, rich in nutrients, can be reused as natural fertilizer on the fields. The next stage takes place in large, cylindrical, enclosed units called evaporators. The treated and clean juice enters these units still very low in liquid, with approximately 85% water content. A stream of steam heats the juice to a high temperature. Some of the water vaporizes and is gradually extracted. With each pass, the juice thickens. It circulates from one evaporator to the next, with pressure and temperature decreasing at each stage, allowing evaporation at different boiling points without wasting energy. At the end of this concentration process, a dense, dark brown syrup with a high sucrose content is obtained. This concentrated syrup is then transferred to other vacuum cookers, large pressurized vessels, where heating continues and crystallization begins. At this stage, sugar crystals slowly form within the paste-like mass called meticulous, a mixture of crystals and honey. Samples are continuously taken and placed on a glass slide to inspect the quality and quantity of the crystals formed. To separate the sugar crystals from the residual honey, the meticulous is sent to centrifuges. The hot, viscous mass is pumped into the rotating basket, which begins to spin at very high speed, exceeding 1,000 revolutions per minute. Centrifugal force throws the crystals against the basket walls, while the molasses is expelled through fine orifices and collected separately. To further clean the crystals, a jet of hot water or steam can be applied inside the centrifuge, washing the grains without completely dissolving them. The sugar crystals are then removed from the drum and directed to the drying stage. This phase eliminates residual moisture from the crystals exiting the centrifuge and prevents clumping, ensuring a free-flowing, stable final product ready for storage or packaging. The sugar is distributed in a horizontal drum. As it rotates, a stream of hot air, around 70 degrees Celsius, blows through it from below or inside the cylinder. This air quickly removes moisture, while regular stirring ensures that all the grains come into contact with the hot air and that the sugar does not form clumps or begin to caramelize. After drying, the sugar remains warm and could absorb ambient moisture. It then passes through a cooler, where it is exposed to a stream of cold, dry air. Now the sugar is ready and conveyed to storage silos. A non-perishable product, it can be stored for years, provided it remains in a cool, dry environment. When the time comes, it is directed to the packaging area. For industrial uses, special 1-ton bags called big bags are used. For consumers, sugar is packaged in 1 or 2 kilogram bags. Each package bears the mandatory information: batch number, type, best before date, and origin. The bags are arranged on pallets and ready for storage and transport. For every ton of sugarcane processed, up to 110 kilograms of sugar, 260 kilograms of bagasse, and up to 90 liters of ethanol are obtained. This is how billions of tons of sugar are produced worldwide over the years. If you enjoyed this episode, please give it a like and share it with your friends. Subscribe and turn on notifications to be alerted of each new video. Let us know in the comments where you're watching from and what you thought of the video. Thank you for staying this long, but don't go yet, there's more. The rest of this video will be just as exciting, so stay with us until the end. Dry ice is an amazing material. It doesn't melt in liquids, but it generates a dense mist upon contact with water. It can instantly freeze a strawberry, solidify a dessert in seconds, or preserve vaccines in perfect condition for weeks. Unlike the classic ice cubes we use at home, this special ice isn't made of water. It's made of carbon dioxide. When this gas is cooled and compressed until it solidifies, it takes the form of a white substance reminiscent of ordinary ice. Its main characteristic is unique. When heated, it does not pass through the liquid state. It skips this step and goes directly from the solid state to the gaseous state, a phenomenon that scientists call sublimation. Because it doesn't generate moisture when it evaporates, dry ice is highly sought after for preserving food and medicine. Its mysterious mist has become a staple of special effects at shows and events, and its physical and chemical properties are so useful that it's also used for deep industrial cleaning. But have you ever wondered how dry ice is produced on an industrial scale? In this video, we'll discover together how one of the most fascinating chemical compounds is manufactured and packaged in factories. Stay with me until the end. Dry ice was discovered by accident in 1835 by French chemist Adrien Jean-Pierre Tillorier. Tillorier was working with liquid carbon dioxide in a high-pressure container. When he opened the cylinder, some of the liquid evaporated very quickly, and what remained turned into a solid white mass, what we now call dry ice. Despite this early discovery, its practical use didn't really begin until about a century later. It was in the 1920s that chemical companies in the United States began producing and marketing dry ice. At that time, it was mainly used to preserve food during transport, especially meat and dairy products. Its strength was that it maintained a very low temperature without leaving water residue as ordinary ice would. During the Second World War, its role became even more important. Dry ice was used to preserve vaccines, medicines, and food supplies for troops, contributing to medical and food logistics in times of conflict. What distinguishes dry ice from conventional ice is its direct solid gas behavior, sublimation, which prevents the formation of water and residue. Its extremely low temperature, around minus 78.5 degrees Celsius, makes it a preferred tool for refrigeration when conventional means are lacking. Its main function is to maintain materials at low temperatures where there is no refrigeration infrastructure. A notable example is the transport of organs for transplantation, such as the heart, which must remain at a very low temperature throughout their journey. Dry ice is also used to transport vaccines or any type of sensitive biological material. It's ideal for maintaining stable and safe thermal conditions. If you immerse dry ice in hot water, the carbon dioxide is released very quickly and creates a thick cloudiness, hence its spectacular special effects. But now let's look at how it's made. How do you get this otherworldly ice cream? It all starts with pure carbon dioxide, which is extracted and processed from various industrial sources. One common process is capturing CO2 from sugar fermentation during alcohol production in breweries and distilleries. This gas, produced in large quantities, is captured, purified, and then stored. Carbon dioxide can also be recovered as a byproduct during the synthesis of ammonia, a major component of fertilizers, and is captured before being released into the atmosphere. Some refineries also release CO2 when converting hydrocarbons into fuels and chemicals. It is even possible to recover carbon dioxide from the combustion of fossil fuels in thermal power plants. But be careful, CO2 from these sources often contains impurities that must be removed to ensure safe quality for dry ice production. The first purification steps involve filtering out solid particles and removing coarse impurities using mechanical filters. The gas then passes through scrubbers and other treatment systems where chemical compounds, vapors, and residual contaminants are removed. Once purified, the carbon dioxide is compressed to a pressure of about 15 bar, a pressure that corresponds to what one would feel about 150 meters deep under the sea. Under this high pressure, the CO2 is cooled to temperatures of around -20 to -30 degrees Celsius and then remains in a liquid state. In its liquid state, it becomes much easier to handle, transport, and store in specially designed tanks. The purified carbon dioxide is then stored in cryogenic tanks designed to withstand both high pressure and low temperatures. These tanks, often cylindrical and made of stainless steel to prevent corrosion, are equipped with valves and safety devices to prevent overpressure. They are maintained at sub-zero temperatures to limit CO2 evaporation. In some facilities, the total storage capacity can reach 2,600 tons of liquid carbon dioxide. From these tanks, liquid CO2 is transported by pipeline to the production units and specialized dry ice manufacturing machines. This is because carbon dioxide at high concentrations can be asphyxiating for workers. All facilities have continuous ventilation, alarm, and monitoring systems to control gas levels in the air and ensure operator safety. In the production machine, liquid CO2 is subjected to controlled decompression. The pressure is abruptly reduced to approximately 5 bar. This rapid reduction in pressure causes a sudden drop in temperature, resulting in the formation of carbon dioxide snow. During this expansion, the CO2 absorbs thermal energy from its surroundings and cools instantly. Some of it then becomes solid in the form of fine particles, known as dry ice, while another part becomes gaseous again and is evacuated through a ventilation system. The dry ice is deposited in a collection chamber inside the production machine. It accumulates as a white light, powdery powder, very similar to real snow. However, in its powdered state, it is not yet usable as solid dry ice. It needs to be compacted. To obtain solid blocks, the snow is transported to hydraulic fields that exert considerable pressure. Large quantities of CO2 snow are introduced into a rectangular mold. Then a hydraulic piston applies pressure of up to 300 bar. Under this stress, the snow particles bond together and form a compact and strong block. The block is thus formed at a temperature of approximately -78.5 degrees Celsius. It is then ejected from the mold and cut to the desired dimensions, according to customer requirements. Large blocks, smaller pieces, or pellets, small solid cylinders that are very practical for certain applications, can be produced. Pellets are generally manufactured in 2 common sizes, 16 millimeters in diameter for use in refrigeration and transport, and 3 millimeters for more specific uses such as dry ice cleaning. To make pellets, CO2 snow is forced through an extruder equipped with perforated dies. A mechanical piston forces the snow through the holes, and this pressure-driven shaping produces solid cylinders at the outlet. Depending on the diameter of the extruder's holes, pellets are obtained in sizes 16 millimeters or 3 millimeters. 16 millimeter pellets are often preferred for packaging and transporting low-temperature products. The finer 3 millimeter pellets are used for dry ice blasting, also known as dry ice jetting, or as raw material for making larger blocks. After compaction, dry ice remains at an extremely low temperature of approximately -78 degrees Celsius and must be handled and stored in a suitable environment to prevent premature sublimation. Since carbon dioxide is both an expensive raw material and considered polluting in some contexts, industries seek to recover and recycle as much of the gas released during production as possible to reduce losses and environmental impact. Once production is complete, the blocks and pellets are transported by conveyor to the packaging area. At this point, laboratory checks are carried out. Weight, size, density, compaction. These are all factors that influence the product's strength and ability to resist fragmentation during transport. The product's purity is also analyzed to ensure it meets commercial quality standards. After passing these tests, the finished product is ready for storage and distribution. One of the main challenges associated with dry ice remains its transportation. Since it undergoes continuous sublimation, it tends to gradually disappear. To limit this loss, enormous insulated polystyrene boxes are used, real portable glaciers, which act like refrigerators and limit the conversion of the solid into gas. The goal is to maintain temperature and minimize sublimation, which can be around 5 to 10% per day, depending on environmental conditions. ambient temperature, insulation, container opening, etc. The final product is therefore packaged in its thermal containers, ensuring its preservation before distribution to customers, sometimes on the other side of the world. Because dry ice reaches temperatures close to -78 degrees Celsius, it is generally not necessary to place its crates in electrical refrigeration systems. Dry ice remains cold and solid on its own, provided it is stored properly. Dry ice is used in a wide variety of industries today. In the food industry, it ensures that food arrives frozen where it needs to be, from frozen products to perishable goods. In hospitals, it preserves vaccines, biological samples, and even organs intended for transplantation. In industry, pellets are used in cryogenic cleaning operations, allowing machines and molds to be stripped or cleaned without leaving chemical residue. And of course, in the entertainment world, dry ice produces the iconic fog that enhances shows, concerts, plays, and film productions. Thanks for staying here. If you enjoy this documentary, then don't forget to like, subscribe, and hit the bell so you don't miss any of our content.